Good morning, everyone. I would like to recap a bit what we did yesterday. So we started out discussing rather elementary stochastic processes, and as the first example, I looked at the simple random walk, where you have a particle on a one-dimensional lattice, and this particle can hop forward with a rate p and backward with a rate q. And what we calculated just by calculating the moments of the distribution, we saw that the mean is increasing linearly in time with a speed v, and the speed v is related to the basic length scale divided by the basic time scale times the difference between the forward and the backward hopping rate. Okay? For the variance, we also found that this is linear in the time with a coefficient that we call the diffusion coefficient, and that diffusion coefficient is related to the variance of one of the hops, and you can write this as the product of p and q and the square of the length scale divided by the time scale. Okay? And you see that if you look here at this graph, what you see is that here you have a linear increase. This is the mean, and then the dashed line you see that gives the width of the distribution. And then we said, well, let's take a closer look into the statistics of the problem. And well, you can simply write down a binomial distribution because it's a Bernoulli process with a success probability and the complement to it. So this is the full distribution function where you have p and q to the respective forward steps and backward steps, and the binomial factor counting how many for the trajectories you have for a given number of forward and backward steps. And one important conclusion was, and I didn't show you that, it's something you can look up in statistical physics books, is that these distributions, they converge to a Gaussian distribution, where the only two important features that enter the Gaussian distribution is the mean and the variance, and of course the shape of the Gaussian distribution. So it's enough to know the mean and the variance to fully know the distribution function. And as we discussed, this distribution is valid only at the core of the distribution function, not at the wings, and for a long time. So you see that this histogram here, where is it? So here you have in blue the histogram obtained from simulations, and in black you have the binomial distribution. And I didn't draw the Gaussian distribution, but it would look similar to the binomial distribution, but only in the core of the distribution function, not here on the tails to the left and to the right. Okay, and well, what else wanted to show you? If you then look at the time evolution of that, you can also write it like so, where you now really write position and time and velocity. So you have here an exponential distribution, and you see this distribution function is progressing in time, so it moves forward at an average speed, and at the same time as it moves to the right, the width of distribution is also increasing linear in time. And those are the two hallmarks of a Gaussian process, a mean speed and a variance that grows linear in time. Are there questions to that? Okay. If not, then let me continue. So what I wanted to do next was to look not at a simple random walk where we had discrete random variables, but at what's called the Gaussian random walk. And the difference now is that the jump size is no longer a discrete variable between plus a and minus a. It's a continuous variable. So what we have is then that the update of the position of our random walker is the previous position plus psi t. And as you know, you can write this as the sum over all times t prime equal 1 to t, where I choose now my time scale to be 1. So I'm measuring times in units of tau. And importantly, as I said, this psi is no longer a discrete variable. It's a continuous variable. So I specify the distribution function of the range of the hops, and I assume it's to be a Gaussian distribution. So I assume it to be Gaussian with a width given by the standard deviation sigma t. Okay? And that needs to be normalized, this Gaussian distribution, and that means just copying what I have from above. This has to be multiplied by 1 over 2 pi and the square root of sigma t squared. Okay? So it's kind of like saying, previously when you look at a discrete random walk, you see that at long time scales in the core of the distribution function, you get a Gaussian distribution. And now I'm saying, I'm assuming that already at the scale of each individual hop, you do have a Gaussian distribution. Okay? And then we want to work out what is now the distribution function of xt. Okay, and as a spoiler, if you have Gaussians and you add Gaussians, you always get Gaussians. Okay? And we'll see this now explicitly as we go through the calculation. Okay, and note that now I specified something that has no drift. This is diffusion only. There's no a deterministic part that will move the distribution in one direction. So let's do the calculation for the moment first. The average of the random walker is this sum that we have from t prime equal 1 to t, averaging the psi, the hop sizes at times t prime, and obviously there's a Gaussian distribution. It's symmetric to the right and to the left. So plus and minus appears with equal probability, so that must be 0. Okay? If we take the second moment, and now note the second moment is the same as the variance because the mean is actually 0. So this is the variance. And as before, I can calculate this by this double sum over t prime and t double prime from 1 to t, psi t prime and psi d double prime. Now in that case, if you divide up the sum into those parts where t and t prime and t double prime are the same and different, in that case, if they are different, I can separate, but each average is 0. Okay? So the only term that remains is the one where t prime equals t double prime. So that's then the sum t prime equal 1 to t. The step size squared. Okay, that's something we know. This is now the variance of the distribution that I assume about the individual jumps. And that has a variance which is given by the standard deviation squared. So this is sigma t prime squared, and I'm summing from t prime equal 1 to t. And that's already an interesting statement. You have a Gaussian, you have a sum of Gaussians, and the sum of Gaussians leads to the fact that the variance is also the sum of the variance of each individual Gaussian that you have. Okay. Good. Now we want to not just know the moments, we also want to know the full distribution. And there are various ways of getting that. As always in all these different stochastic processes, there are many ways to arrive at the same result. And what I'm doing in the last lecture and now in the following lectures, I'm giving you various ways, different ways of calculating things. Okay? So now what I do is I'll define what's called a characteristic function. So it's a function, chi, for the stochastic variable xt as a function of a parameter s, and it is defined as e to the is xt average. Okay, so it's the statistical average of a phase factor containing my random variable. That's the usual definition of a characteristic function. I'm not sure you have seen that, but that's the standard tool that you have in classical probability theory. If you haven't seen this, this is in this language here. You can also read this as a kind of Fourier transformation of the distribution function. Okay? This is the same thing. All right. Now, since each step is a Gaussian distribution, I can write down the corresponding characteristic function, not for the full random walk, but just for each individual step. It's the same kind of construction. Now I have psi t instead of xt. Well, and the calculation is really, you write out the brackets. The brackets mean that you integrate over this distribution function, right? This distribution function is a Gaussian, so it's quadratic in the exponents. And then as you multiply it with this here, you get a quadratic form in the exponent. You can complete the square and use the formulas for Gaussian integration to get the corresponding result. You find this in my notes. It's a very elementary calculation. You can also say that for these Gaussian variables, to take the average of the exponent of something, you get the exponent of the variable that you have here squared divided by 2. And that's what you find. So you find this is a half, and the square of what you have here, that's why you have a minus. You have s squared, and then the average of psi squared is sigma t squared. Okay? So reading this says, if you want the characteristic function of a Gaussian distribution, of a random variable that has a Gaussian distribution, you find that this has a Gaussian form, a quadratic form, but now the sigma t that used to be in the denominator of the Gaussian distribution has been moving up to be in the numerator. And that's just because you have been completing the square to calculate this Gaussian integral. All right, now we have that. So that's the characteristic function for each step. Now let's use that result to calculate the characteristic function of the full stochastic variable. So I have to write in the exponent now a sum over all the different step sizes and take the average. Well, this is the same, and I'm now really explicit in what I do here. This is the product from t prime equal 1 to t, e to the is psi t prime. Okay. Now what's the next step? Yeah.
They're independent, so you factor the expectation?
Yeah, so you can draw it in, right? So you can move this bracket in because of statistical independence. So let's do that. All right, this is the same as this. And now I'm back to what I had. Okay, so I can copy the top line, and that's then the e to the minus a half s squared sigma squared, and I again move the product to the sum. So I'll get the exponent of minus a half s squared, and all that changes, you have the sum from t prime to t, sigma of t prime squared. So it just means that for the Gaussian process, the characteristic function, instead of being the characteristic function of a single step, it's the product of the characteristic functions that you have, yeah?
Will we be looking at examples where we cannot take out the sum out of the averaging step?
Yeah, they are more complicated. Okay, the question is, will we also look at examples where there's no statistical independence? Of course we will. But right now, I'm focusing on the simplest cases. Okay? Well, then life becomes complicated because all these formulas are not really applicable anymore. All right, so now we have the characteristic function. How do we get the distribution function? Just have to think backwards, right? So we know that this here has a Gaussian distribution as the distribution function. So this one will also have a Gaussian as a distribution function. All I have to do is I replace sigma t squared by the sum over all sigma t prime squares from t prime equal 1 to. So let me define then the full sigma squared. Now for my random variable xt, this is then the sum from t prime to 1 to t, sigma t prime squared. That's my definition. And then the probability distribution of my random variable xt, assuming a value x, which I can also write in shorthand as px and t, is the Gaussian for the full variance, so 2p sigma squared t e to the minus x squared over 2 sigma squared t, right? So here we are, and if you compare it to the formula that we obtained starting from a simple random walk in the limit of the central limit theorem, that's the same result. Okay? So in a way, the Gaussian distribution is a fixed point of a random walk, independent of how you really construct the microscopic details of the random walk. In the long run, you will arrive at a Gaussian distribution, which is kind of the universal behavior of a random walk. Okay? If you want to learn about renormalization group theory approaches to this random walk, which is really a very elementary discussion of renormalization group theory applied to this very basic problem of random walk, I recommend that you read an article by Ariel Amir. Ariel is at the Weizmann Institute, and the link to the corresponding paper you can find in my lecture notes. It's a very illuminating discussion that you will find there. Okay, so that is the conclusion for the random walk, the Gaussian random walk. And now let me move on to the next chapter, which is the so-called Poisson process. And before I start discussing the math, let me motivate why this is an interesting problem. All right, so, and before I forget, this is not just an interesting problem that you can solve analytically. This Poisson process will also form the foundation for us to define the most important algorithm in stochastic dynamics, which is the algorithm due to Gillespie. Okay. So let's start. Here's my motivation. What you see there is a microtubule. For those that don't know biology, a microtubule is a fiber in your cells. This fiber is responsible for organizing the cytoskeleton of a cell. It's helping to divide cells into two. And it's also a highway for molecular motors. This thing is very thin. It's just, say, 5 to 10 nanometers in diameter. So it's really a nanotube, a hollow nanotube with a lot of different lanes called protofilaments. Roughly you have 12 lanes. So you can think of this as a circular highway. And on that highway, you have molecular motors. Here, those guys. This motor has a name. It's called kinesin. It has two heads. They're actually functioning like legs. They are attached to monomers of this microtubule structure. The black dot here and the white dots, they're monomers. You see they're 8 nanometers apart. And now as the system is using chemical fuel in the form of ADP. ADP cycle is the basic cycle of energy fuel in your body. If I get the numbers right, the turnover of ATP in your body is something like 30 kilos a day. Not that you're losing 30 kilos by ADP, it's the turnover, the number of molecules that make that turnover. So it's really a major source of energy in your body. Yeah?
What do you mean by turnover? 30 kg?
Turnover, I mean that a molecule goes through a cycle of ADP to ATP and phosphate. And does this again and again and again. And that happens in your body all the time because you have to flex your muscles. All the processes in your body have to function. And this uses as many cycles that would correspond to 25 or 30 kilos of ATP. So it's really a massive energy source, and it's used to move motors. And here this is a cartoon movie. It's created by the people that you see here on the bottom. And here you can see what happens. So these are these two heads or legs of the kinesin motor. It's an artistic view. You have an exchange of ADP through ATP. Then you have a conformational change of the motor heads. Then you have hydrolysis happening on the back. You have exchange of ATP and ADP in the front. And this repeats and repeats. And by that, this molecular motor moves forward. Of course, this is a movie. This is not a real simulation. The real thing is much more random and stochastic than this deterministic motion that you see there. But I wanted to show you that to kind of see that each of these kinesin motors in your body moves along the microtubule like on a highway.
Sorry.
Yeah.
What kind of time scale is this? How quick is it?
This is very fast. So I'll show you a movie then of the speed. So this is now a real system, which is an experiment done by the lab of Joe Howard at Yale. And what you see here is the following. You see the microtubule. That's the structure here in red. This is labeled by a fluorescent dye. And then you also see these green spots here. And there again, these are the motors where you have attached a green fluorescent dye to the molecular motors. You can really see them. Then let's start the movie. I think it's real time. So here you see how these motors move along a microtubule. The scale bar is 2 micrometer. So you see that's the speed of these motors. Okay?
How much time is one frame? Because
I said it's roughly real time. So you see this runs on a time scale, a speed of micrometers per second. Yeah, that's the typical speed. That's a macroscopic observation of what happens there. So this is the observation, and now you ask yourself, it's a complicated biological process, right? There's an exchange of ADP and ATP, there's conformational changes of these motors. There's a lot of details that you see there. And how can we abstract this motion to a simple model that still captures the main features of this dynamic process that you see in nature? Okay, and the idea is the following. To replace this by a process where you have a particle hopping on a lattice. The lattice is motivated because you have a microtubule with the binding sites being the monomers of these protofilaments that you have. Okay, so you just make a lattice of 8 nanometer distance between the binding sites. I simplify because I say I approximate the motor with its two legs as one object. Okay? And this one object is this red particle that you see there. And I'm saying, let's assume there's not this detailed motion that you saw in a movie, but this particle, the motor, is hopping forward from one side to the next side with a certain rate that I call nu. It's the hopping rate. And I neglect any kind of backward steps because, as you saw in the movie, the backward steps of this chemical process that makes the motor run are very unlikely to happen in the backward direction. Okay? Now let's see how far we get with that description. Okay? That's my motivation. And this process is called a Poisson process. All right? Now, yeah, that's what I said already. Particles, the motor moves in one direction only, but stochastically. There's a probability per time, which is the rate. This is nu. And, well, this I do on the board. So please ask questions if you still have some. Okay? So, yeah?
But muscle is moving so quickly. How come the time scale is micrometer per second?
You have to think about a collective process of a muscle moving, where there's many motors, not called kinesin, but myosin, and they slide actin filaments with respect to each other as you flex your muscles. And it's this collective motion of these many motors in a macroscopic structure, and not just the motion of a single motor along a microtubule. So since you know it, so if you have a kinesin that walks on microtubules, it's really walking on it, and it's rarely detaching and attaching. The myosin in your muscle is also a motor, and it attaches to the actin filaments, does its power stroke, and then detaches. So it's more like rowing, the way a muscle works, than like walking in the case of kinesin. Right? So now let's come to the mathematical description. So we do have this Poisson process. That means we're going back to the mathematical description now. I have a side n. I have a side n plus 1. I have a side n minus 1. I have the particle here, and it hops forward with a rate nu that I call the hopping rate, and this is a probability per unit time. So if I fix my time scale to a small increment dt. Oh, and by the way, I didn't say that, but I should. Before, when we looked at the random walk, we said that time is progressing in increments, in increments of tau. Now my time is running continuously, as it usually does. So I'm specifying the process not by a probability, but by a rate. And I get a probability if I fix a time scale. And what I'm doing now is I say my time scale is a small, very small incremental time scale delta t, infinitesimal. Then I have a corresponding probability, p plus, of my particle hopping forward. This is the rate times the time scale that I'm looking at the process. Okay? There's an alternative, as this is hopping forward. What's the alternative? You can't hop forward, you can't hop backward, I excluded that, but you can, stay lazy and stay put. So you have P naught is the probability of not hopping, and that's 1 minus nu times dt. That's not moving or staying at the site where you are. Okay, it's as simple as that. It's a continuous time stochastic process. Where time is now a real variable, but it's still a hopping process, so it's discrete in the stochastic variables. My stochastic variable, n of t, is the position of the walker at time t, and that is my random variable, and this is element of the natural numbers. Let's say I'm starting counting at 0, and then things just move in the forward direction. What you get as a trajectory in that case, you will start with, let's say, our particle being at position 0 at time 0. That's a convention. And now I'll have to figure out not just what the next step is, but when the next step happens. And that's time t1, and etc. So you might then also have a time t2 where you hop forward, and all in between you stay put. That's my stochastic trajectory. It defines the time instance where my particle, my Brownian, my Poisson stepper or the molecular motor hops from one binding site to the next binding site. So now we have that problem. We can ask quite a few questions concerning the outcome of that stochastic process. Okay, and I'll list it for you, and then we'll go through it step by step. So what questions can we ask? Well, the first one you have to ask is, what's the waiting time for the next step to actually happen? We have defined the process with a rate, nu. Can we even calculate the distribution function of the times for the next step? That's the first question. Waiting time distribution between steps. What else could you ask? It's a question for you. Come on, don't be shy. Yeah?
The distribution of n of t for given t?
Yeah, that's one, for sure. So we can ask, as before, the probability that our random variable takes on a certain value. And that's asking, right? I'm fixing time, and I want to know what's the probability distribution at a given time of observation. How far did my particle come on average? What's the variance? What's the distribution function at a given time? What else can you ask? many questions you can ask. So I'll tell you, one question you can ask is also, when do you get at a particular site first? Okay? So you're not asking, given a time, how far do you go? But given a position, how long does it take you to get to that position? And that's a first passage time problem. So you can ask about first passage times. All right. And that's the three questions I would like to go through with you now. Yep.
Is this problem also called stopping times?
Stopping times may be related to that. I'm not sure what you mean exactly by stopping time.
I heard it in math literature about stochastic processes. It's felt related, but
Yeah. Maybe, I don't know the term exactly, but it sounds like similar. Yeah. Stopping time may be also that you have certain criteria of a process to fulfill, getting over a certain value, and then you want to stop the process because otherwise something bad happens on a queue or so. That might be the problem. Then it's a first passage time problem. All right, now waiting times. Distribution. So again, as always, when you think about a stochastic process, you need to say, what is your stochastic variable? Now my stochastic variable is the waiting time. How long does it take for me to step forward? And I can define a cumulative waiting time distribution. Let me write it down. So it's the probability that my waiting time t is less than a given time t. Okay? That's a cumulative distribution function for my stochastic variable. I can look at the opposite of this, w bar of t, which is the, well, let's take this also with the equal sign, the probability of t being larger than t. Now, what is that? This means that at the time t, nothing happened, right? Because my waiting time is larger than the time t I'm looking at. So this distribution function is the survival probability at time t, meaning the probability that the Poisson stepper did not move. And that's what I call survival probability, because I have in mind that there is some kind of death to a certain state. Okay? And so let me call this the survival probability. Or you also say no step until time t. That's the same thing. Okay, and now we use a concept that's often used in the theory of stochastic processes to derive a functional form of a probability distribution function. And this approach is kind of divide and conquer, meaning you try to dissect your stochastic process into small time increments and then derive from the dissection of the stochastic process into small increments a differential equation, and from that differential equation then calculate the distribution function. So let's do that. So let's ask, what is the survival time, a survival distribution, not at time t, but a little later, at the time t plus delta t. Okay? So you know this is the probability as I defined it, that t is larger than t plus delta t now. And you can divide this up. You can say, this is the probability that I survive until time t, right? And then later, between t and t plus delta t, I do not hop. Okay? So that means t larger than t and no hop in the time interval between t and t plus delta t. So it's two events that have to be there simultaneously for no event to be happening in time t plus delta t. Okay, now again, as before, this is now a particular case again, we use statistical independence. The walker, if it hops at a certain time, the next step is statistically independent of what happened before. And that's what I'm using here. The time to survive until time t is statistically independent of hopping forward in time t plus delta t. So I'll write this because I know the statistical independence as the probability of surviving until time t times the probability of not hopping. What's that? Yeah?
1 minus nu dt.
Yeah, 1 minus nu dt. Okay? And this here, right, is s of t. That's the same thing. Now you bring the s of t on the other side. You divide by delta t. And then in the limit of delta t small, you get ds dt equals minus nu times s of t. Okay. So here we go. That's the differential equation we derive for our survival probability. We can solve this differential equation quite easily. I've done this many times during different classes. You need, of course, an initial condition. What's the initial condition? So at time equal to 0, the survival probability is, of course, 1. Nothing can happen in no time. So S of 0 is 1, and that means if I solve that relation, I get exponent minus nu t. Yep.
Does this somehow mean that it can't hop twice at the same time?
Yes, because we are saying that we make this dt small enough such that this will not happen. So mathematically, you can say that the process has to be such that in infinitesimal time, at most one event can happen, and the other event, the second event at the same time, is not possible. Okay? And that makes sense, perfect sense in terms of physics, right? If you make time smaller and smaller, and you make it infinitesimal, smaller than all the microscopic time scales that define the molecular process the motor takes in order to move from one side to the other, once you're below that, you cannot have something happen twice at the same time. That doesn't work. Yeah. All right, so this is quite an important result because it says there's an exponential distribution of waiting times and this exponential distribution of waiting times, if you calculate the mean, it's 1 over nu, so equal to tau. And if you calculate the variance of this exponential time, it's 1 over nu squared, so it's tau squared. And that matches with, especially the result on the mean matches with what we did here in defining the process, right? Remember, we said there is a hopping rate, which is a probability per unit time to move forward. So expect that the waiting time to the next step goes like the inverse of the rate. And that's what you see here. The typical waiting time to the next step is the inverse of the rate, which I define to be tau now. And the variance, you can just calculate, that turns out to be 1/nu squared. All right, with that, I think we go into our break. But before, are there questions still? All right, so let's have a break till 1/4 past and then reconvene.